Section. Introduction. We're going to talk about simultaneous translation, which is a method that aims to speed up machine translation systems. Instead of waiting for a speaker to finish their sentence, a simultaneous translation model starts translating while the speaker is still talking. This is particularly useful in situations where real-time translation is needed, like during international conferences or personal travels. Unlike offline models that translate a whole sentence in one go, simultaneous translation models work on parts of a sentence. They use a policy to decide when to start translating. This policy has two actions, read and write. Read means the model pauses to gather more information, while write means it starts translating. These policies can be rule-based or learned through training. Recently, a type of learned policy called monotonic multihead attention, MMA, particularly the transformer-based version, has shown excellent results in simultaneous text-to-text translation tasks. MMA uses an unsupervised policy learning framework that estimates monotonic alignment during training. However, when applied to speech input, MMA doesn't perform as well. This is due to the unique characteristics of speech encoder states. In this paper, we delve deeper into the use of monotonic attention in speech translation. We identify two main reasons for its underperformance. The first is the numerical instability and bias introduced during monotonic alignment estimation. The second is the high variance in monotonic alignment estimation, especially towards the end of a sentence, due to the continuous nature of encoder states. To overcome these challenges, we propose a new model called Efficient Monotonic Multihead Attention, EMMA. Our contributions include a new, numerically stable, unbiased monotonic alignment estimation method, a new strategy for shaping monotonic alignment, and an improved training scheme. Now, let's talk about the basics. In a translation system, we have input and output sequences, denoted as X and Y hat. X is the text token for text input and speech encoder states for speech input. We also have a delay sequence, D, where each element, D_I, is the length of input used to generate the corresponding output element, Y hat_I. D is a strictly increasing sequence. In a simultaneous translation system, there exists a Y hat such that D_I is less than the length of X. In an offline translation, D_I equals the length of X for all I. In this paper, D_I is measured in tokens for text input and seconds for speech input. We evaluate simultaneous speech translation systems based on quality and latency. Quality evaluation is the same as for offline systems. For latency, we use a metric called average lagging, AL. This is the average delay between the time a word is spoken and the time it's translated. Monotonic attention models have a learnable policy based on monotonic alignment estimation during training. At a given time, when the I1th target translation has been predicted and the JTH source input has been processed, a stepwise probability, P_I, J, describes the likelihood the model will write the ITH prediction rather than read the next input. This is defined using the policy network, the I1th decoder state, and the JTH encoder state. There are also methods to estimate alignments between source and target from P_I, J during training. Some models introduce soft attention in a chunk following the moving attention head, while others compute soft attention over all the previous history. These models also introduce latency-augmented training for latency control. Some extend the monotonic attention to multihead attention for transformer models, enabling every attention head as individual monotonic attention. Section Summary. Simultaneous translation is a technique that aims to reduce the latency of machine translation by initiating the translation process before the speaker completes their sentence. This approach operates on a partial input sequence and incorporates a policy mechanism to determine when to generate translation output. However, when applied to speech input, the existing model, known as transformer-based monotonic multihead attention, MMA, faces challenges due to numerical instability, bias, and variance in monotonic alignment estimation. To address these issues, this paper proposes efficient monotonic multihead attention, EMMA, which provides a numerically stable and unbiased monotonic alignment estimation, reduces monotonic alignment variance, and achieves state-of-the-art performance in both text-to-text and speech-to-text translation. Section. Efficient monotonic multihead attention. In this section, we'll delve into the three main aspects of efficient monotonic multi-head attention, EMA: numerically stable estimation, alignment shaping, and streaming fine-tuning. It's important to note that the monotonic alignment estimation, symbolized as alpha, discussed here is based on a single attention head. This estimation is applied to every attention head in MMA, as incorporated into the transformer model. We only use the infinite lookback variant of monotonic attention. The goal of the monotonic estimation is to calculate the expected alignment, represented as alpha_I_j, from the stepwise right action probability, denoted as P_I_j. However, the calculation can become unstable due to the denominator in the equation, especially when multiplying several small probabilities. To solve this, we propose a new numerically stable method for estimating monotonic attention. The monotonic alignment between the ITH target item and the JTH source item can be represented as a matrix multiplication, where T, I, is a transition matrix. Each element of this matrix, T, I, underscore, M, N, represents the probability of the policy at the I1, TH target step skipping from the MTH to the NTH inputs in sequence. This transition matrix can be further expressed in a different form, which can be efficiently executed in parallel on GPUs. This estimation process is closed form, meaning it's numerically stable and unbiased, as it doesn't require a denominator as the product of probabilities within the equation. When training the infinite lookback variant of monotonic attention, it's necessary to add latency regularization to prevent the model from learning a trivial policy. Without this, the model would read the entire sequence before starting the translation, which is not optimal. Therefore, we applied latency and variance regularizations to balance translation quality and latency of the learned simultaneous translation policy. The latency of the alignment describes how much partial input information the model needs to generate part of the translation. The reduction of latency is commonly achieved by introducing a regularization term derived from the estimated alignment. The expected delays are estimated from the expected alignment during training time. The expected delay of target token Y_I is computed as a certain formula. Given a latency metric C, the loss term is then computed as another formula. The variance of the alignment characterizes the certainty of an estimation. An alignment estimation can be low latency but high variance. For example, a random walk policy, which yields a monotonic alignment of linear latency, has a large variance on the estimation. We propose a method to reduce the uncertainty by introducing a Gaussian noise to the input of stepwise probability network. However, empirical results show that this method is not efficient, especially when applied to speech translation models. Therefore, we propose an alternative regularization-based strategy. The expected variances of the monotonic alignment are denoted as V. The expected variance of target token Y_I can be expressed as a certain formula. We then introduce the alignment variance loss as another formula. To further reduce the alignment variance, we proposed an enhanced stepwise probability network. This network serves as energy projections, constructed using multi-layer feed-forward networks, which increase the expressive capability of stepwise probability network over linear projection adopted by prior monotonic work. In most prior work on simultaneous translation, the model is usually trained from scratch. However, this approach often requires substantial resources when dealing with extensive or multilingual scenarios. For instance, it can be a significant challenge to retrain a simultaneous model with the configuration from recent large-scale multilingual models. To leverage the recent advancements achieved with large foundational translation models and enhance the adaptability of the simultaneous translation model, we introduce a method for simultaneous fine-tuning. The simultaneous model is denoted as M, theta_E, theta_D, theta_P, where theta_P denotes the policy network. Simultaneous fine-tuning involves initializing theta_E with theta_O_E and theta_D with theta_O_D. During the training process, the encoder parameters theta_E remain fixed, and optimization is only performed on theta_D and theta_P. This design is motivated by the assumption that the generative components of the model, namely theta_E and theta_D, should closely resemble those of the offline model. In simultaneous setting, they are adapted to partial contextual information. Section Summary. In this section, we discuss three key factors of efficient monotonic multi-head attention: EMA, numerically stable estimation, alignment shaping, and streaming fine-tuning. We introduce a numerically stable approach for estimating monotonic attention, which avoids numerical instability issues. We also discuss the use of latency regularization and variance regularization to control the trade-off between translation quality and latency in the learned simultaneous translation policy. Additionally, we propose a method called simultaneous fine-tuning to leverage recent advancements in large foundational translation models and enhance the adaptability of the simultaneous translation model. Section: Streaming Inference. We've developed a method for real-time interpretation, using a tool called SimulEval to construct the inference pipeline. This process involves continuously updating the entire encoder each time a new piece of speech data is received by the model. Then, the decoder generates a partial text translation based on a specific policy. We tested our models on a task that involves translating speech to text. We used the SimulEval toolkit to evaluate the models, focusing on two main factors: the quality of the translation and the time it takes to produce it. We measured the quality by using the SacreBlue toolkit to calculate the BLUE score, a standard metric for evaluating machine translation. The latency, or delay, was measured by average lagging, AL. We used a strategy called simultaneous fine-tuning to initialize the simultaneous model from an offline translation model. We provide detailed information about the tasks, evaluation datasets used in this study, and the performance of the offline model. For the speech-to-text translation task, we set up two experimental configurations: bilingual and multilingual. The bilingual setup was designed to show the model's potential when given a large amount of training data. We trained one model for each direction, Spanish to English and English to Spanish. The multilingual task was designed to show the model's ability to quickly adapt from an existing large-scale multilingual translation model, called Seamless M4T. In the bilingual setup, we started the offline model with a pre-trained Wave 2 VEC 2.0 encoder and M-BART decoder. Then, we initialized the simultaneous model based on this pre-trained offline model. The bilingual model was trained on both supervised and semi-unsupervised data. In the multilingual setup, we started the simultaneous model with the speech-to-text part of an offline Seamless M4T model, trained with the same labeled and pseudo-labeled data, and evaluated the model on 100 English directions. Recent research has focused on a neural end-to-end approach, hoping that a simpler system can reduce errors between subsystems and increase overall efficiency in direct translation. This approach was first applied to text translation and then extended to speech-to-text tasks, showing competitiveness against cascade approaches. Simultaneous translation policies are divided into three groups. The first group consists of predefined context-free rule-based policies. The second group involves a learnable flexible policy with an agent, applying reinforcement learning. The third group features models using monotonic attention, replacing softmax attention and leveraging closed-form expected attention. We present the trade-off between quality and latency in the bilingual setting. Our model, EMMA, significantly outperforms the weight K model in all latency regions in both directions. In the multilingual setting, Seamless M4T EMMA can achieve good translation quality in a much shorter training time compared with training from scratch. We also provide a visualization of the policy learned from EMMA. With the guidance of latency and variance regularization, the model can learn a monotonic policy aligning input speech and output text.